Next up, we have impulse. The symbol for impulse is J, and impulse is what you get when you apply a force to an object over time, and it's just equal to the force applied times time. It's a vector. It points in the direction that the force points, and the units are then newtons times seconds. Newtons times seconds are actually equivalent to the units for momentum, kilograms times meters per second. And that's important because impulse is something you do to an object, apply a force over the time, and the impulse that you apply to an object is always equal to the change in momentum. That is, the net impulse is equal to the change in momentum. When this ball hits the wall, there's a rightward force on the ball, and that force is applied for some time delta t. The ball's initial momentum is to the left. The final momentum is to the right after it bounces off. And so the change in momentum is exactly equal to the force times time. And it's also in the direction of the force. It went from a leftward momentum to a rightward momentum. So a couple of practice problems. Let's calculate the impulse experienced by a 65.8 kilogram halfback encountering a force of 1025 newtons for 0.350 seconds. Pause and try and solve that one. Okay, let's solve it. Well, here's my mass. Here's the force that's applied to the halfback, and here is the time. So since impulse is force times time, just calculate it that way. J equals F delta T. That's 1025 newtons times 0.350 seconds. Let me plug that into a calculator. To get 359 Newton seconds is our impulse. Okay, let's try part B. Calculate the impulse experienced by a 0.168 kilogram tennis ball encountering a force of 126 newtons that changes its velocity by 61.8 meters per second. Pause and solve that one. Okay, let's solve it. Here's the mass of the ball, here's the force applied to the ball, and here's the change in velocity. How do we calculate impulse? Well, we need force times time. We don't have time, but remember, impulse is equal to change in momentum, so we can just use change in momentum. Since we're given the change in velocity and the mass, we can calculate it that way. The mass times the change in velocity is also my change in momentum, as long as my mass is constant. So 0.168 times 61.8 meters per second equals 10.4 kilograms meters per second, or newtons seconds. Oops. How about this one? A block of mass 2 kilograms accelerates from a speed of 15 meters per second to a speed of 20 meters per second without changing its direction. What impulse acts on the block? Pause and try to solve this one. Again, two ways to calculate impulse. We can do impulse equals force times time. Or we could do, because we know impulse equals change in momentum, we could do change in momentum, which is just mass times change in velocity. And since we start at 15 meters per second and don't change direction, we end up at 20 meters per second. In the same direction, we can just do mass times change of velocity. It's going to be 2 times 20 minus 15. Final minus initial is our change. So 2 times 5 equals 10 kilograms times meters per second, or Newton seconds. C is correct. So we can also we also need to talk about Newton's second law of motion, which we usually state as F equals ma, or at least we did when we were talking about forces, but this is not Newton's original statement of his second law. The original Newton's second law said force is equal to rate of change of momentum, or delta P over delta T. Now, this is actually Newton's second law, and it's always true. It becomes F equals ma as long as our mass is constant. But we can change momentum in two ways. We could change the mass, or we could change the velocity. And if we think about that altogether, we get we can distribute out that delta. We get forces mass times change in velocity over time, plus velocity times change in mass over time. This lets us deal with systems in which our mass is changing, like a rocket, because as a rocket burns fuel, its mass is going to decrease over time. If our mass is constant, it does simplify to F equals m delta V over delta T, aka F equals ma. And we can rearrange this to get our impulse momentum theorem. Force times time equals mass times change in velocity, or impulse equals change in momentum. So as long as Newton's second law is true, then impulse has to equal change in momentum. So here's an example of two car accidents, one with a bale of hay, one with a wall. And notice that our initial mass, or the mass of the car, and the initial velocity are the same for both. So which is going to experience the greater change in momentum? Well, they both come to a stop, so the change in momentum is the same delta P. Therefore, it's going to be the same impulse. So which one do you want to, which accident would you rather be in? Well, if it's the same impulse, same change in momentum, you might say it doesn't matter, but it does matter, because if you collide with the bale of hay, that impulse occurs over a longer period of time. So if we have a longer period of time with the same impulse, we have a lower force. If that impulse occurs over a shorter time, that means we must have a larger force. So by increasing the length of time of an impact, we decrease the force. Same principle behind a climbing rope, for example. It's designed to stretch to increase the time of the time that it stops you as you fall, and therefore reducing the force on you. So here's another example. A rocket engine uses fuel and an oxidizer in a reaction that produces gas particles having a velocity of 1380 meters per second. The desired thrust is to be 195,000 newtons. What must be the fuel oxidizer consumption rate in kilograms per second? Pause and try to solve this. So we can set up Newton's second law, or we could use impulse momentum theorem. We're given a velocity of the oxidizer particles, and we're given the force that we want to produce. So Newton's second law says that force is rate of change of momentum. And in this case, we're changing my momentum by releasing a certain amount of mass per unit time. So we could write it as force is equal to, well, as it's written above, delta M times V over delta T. And since we're looking for kilograms per second, well, that's delta M over delta T. So we can just solve this equation for delta M over delta T. What do we get? Well, we get delta M by delta T equals force divided by velocity of those particles. 195,000 newtons divided by 1380 meters per second. I'm getting a rate of change of mass of 141, and the units are kilograms per second, because I'm in standard SI. It's a lot of mass burned per second.